his first lecture.
Okay, I should be broadcasting. It sounds like I am. So I still have my organizer hat on for a brief moment. So effectively about 60 seconds from now, I will primarily be a speaker, and so I will be deferring most organizational aspects to the other organizers. But one thing I wanted to do was something that Bryden couldn't do himself, which is thank Bryden and the AWS staff for a tremendous amount of effort putting this together. Okay, so now I'm in speaker mode. So my first thing to do in speaker mode is to tell my story about the AWS. So I was actually a student participant at the very first AWS. Remember, this is the 20th year of the AWS, so my history with the AWS is not completely unbroken, but quite frequent over the years. It's always been a tremendous learning opportunity. Even on the one previous occasion when I spoke, perhaps I learned even more then than the other times, and certainly this time as well. So I hope it will be a formative experience for many of you, as it was for me and as it was for Jared as well. Okay, so maybe I'll say one other thing about my notes. You may have noticed that my notes are a little bit longer than what I can reasonably hope to accomplish in 4 lectures. That was on purpose. I wanted to have the notes be as self-contained as they could be, and to not feel any obligation to go into any niggly details during the lectures. So the lectures will try to provide some kind of guide for how to navigate through the notes. Okay, so let me pick up where Jared left off. So Jared told us about Huber rings. So throughout this talk, A is going to be a Huber ring. I'm not sure I can write with such a thick pen. Let me try a thinner one and see if that still works. So throughout this talk, A is going to be a Huber ring, and as Jared explained, it's convenient to work not just with Huber rings by themselves, these topological rings with this ring of definition, but also with these rings of integral elements. So I will always have a pair called A plus. So I'll call this a Huber pair. So A plus is a ring of integral elements like we had previous hour. And one thing that I'm going to do, which Jared hadn't done yet, but I'm going to start doing this now, is that I'm always going to assume that A is complete for its topology. Of course, that's harmless if you have a ring with a discrete topology, but we're thinking about the sort of rings that occur in rigid analytic geometry, like affinoid algebras, rings of, so things like these rings of strictly convergent power series and one or more variables. So this is, of course, complete for the topology given by the Gauss norm. And so I'm only going to be thinking about pairs in which the A is complete, because these are the ones that I'll need to build adic spaces. So I will also reserve the letter X to mean this space SPA, A plus, that Jared introduced. So you take the continuous valuations on A, and then you impose this restriction that they are bounded by 1 on A plus. Okay? So right now, we have this ring, we have this as a bare set. So the goals for this lecture will be to promote this set to a topological space. Equip it with a sheaf of rings, but I'm giving away the game a little bit here. And then once we've done that, then we can more or less formally form a locally ringed space So this is all parallel to what we would do to go from rings to schemes. We want to turn rings into spaces by building associated topological spaces and putting sheaves of rings, sort of providing functions on those spaces which correspond to the original ring we started with and certain associated guys, which we'll introduce. And then, because I'll need these for my later lectures, I also want to consider certain sheaves of modules over these sheaves of rings. So for instance, I'll be interested in vector bundles, which come from finite projective modules. And, well, in principle, I would like to talk about coherent sheaves, which are supposed to come from finitely generated modules. But already for schemes, one would be wary about this if one has rings that are not Noetherian, so we'll have to be wary about that later. So this is what we'd like to do. We will make some progress with that, but we will also hit some snags, which we will have to work around. To simplify matters a little bit more, let me focus on one of the halves of the dichotomy, or one of the thirds of the trichotomy that Jared mentioned. So Jared mentioned that adic spaces include both schemes and, say, rigid analytic spaces with formal spaces somewhere in between. I want to focus on that part of that picture that corresponds to rigid analytic spaces. So we already understand the theory of schemes and to some extent the theory of formal schemes. So I want to focus on the issues that are specific to the side of rigid analytic spaces and the related objects, because the perfectoid spaces we'll see will show up on that side of the dichotomy. So I'm not going to allow A to be an arbitrary complete Huber ring. So I'm going to assume that A is what's called analytic, which I can say it in a couple of ways. One way to say that is that the topologically nilpotent elements of A generate the unit ideal. So, of course, this is true if there's a single topologically nilpotent element that is a unit. That was the case when A is a Tate ring. This is slightly more general, but it's not a serious distinction. So if you prefer to just think about the Tate case, that would be completely harmless for what follows. I mentioned a couple of equivalent characterizations of this. One is that another way to say this is that every valuation in SPA AA plus is non-trivial. So the definition of SPA AA plus includes the possibility that you have a valuation which has some kernel, but then when you divide by that kernel, you just get the trivial valuation on the resulting ring. It doesn't compare anything except 0. So this condition turns out to be equivalent to saying that there are no such things happening here. So this is somehow, both of these conditions are trying to put us sort of orthogonal to the discrete topology, the case of the discrete topology. Now, of course, things work nicely in the case of the discrete topology because the theory of schemes we know works very well, but when you try to work in between, things get a little more complicated. So I want to stay on the opposite side of that spectrum. One other way you can characterize these rings, as it turns out, these are the Huber rings for which the analog of the Banach open mapping theorem applies. And the statement of that is, well, there are various forms of it. Let me just state one. If I have a continuous surjection, oops. of complete, and I need some topological condition here, first countable topological A modules. So first countable just means that, say, 0 admits a countable basis of neighborhoods so that you can talk about convergence in terms of sequences and not more general nets. So you can ignore that if you don't like general topology. Then F is a topological quotient map. So if you have a continuous surjection, then actually N must receive the quotient topology from M. So this turns out to be, for Huber rings, say for complete Huber rings, this is actually another characterization of this property. So, and this is useful because otherwise you somehow have to worry about not just modules, but also which topology you want to keep track of. And so, of course, when everything in sight has the discrete topology, this isn't an issue. But when you start mixing things, it gets a little bit complicated. So having the Banach-Copen-Mappen theorem avoids a lot of difficulty. So a lot of basic statements in classical rigid analytic geometry secretly use this theorem, but unless you read very closely in the textbooks, you might not notice where it's being used. So it's hiding in the background. Okay. So those are that's my setup. Okay, so what do I need to do? You can still see my goals on the left. So the first thing I need to do is provide a topological space structure on this adic spectrum, this Huber spectrum. So by analogy with the theory of schemes, let me tell you what the distinguished open subsets are that will be used to generate the topology. And, question? Can you give an example of this thing that's not the question was, can I give an example of something that's analytic but not Tate? Yes, but I don't want to do it right now. You can find it in the notes. So there are many examples in the notes that will illustrate things that I don't say out loud. This is part of the reason why the notes got to be the length they did. But yeah, so there will be a number of statements of the form, see the example in the notes. Great. Okay, so let's talk about the topology on the adic spectrum. So this topology was defined by Huber. And this definition is motivated both by the definition of the topology, the Zariski topology on the spectrum of a ring, but also on topologies on spaces of valuations that I suppose were also considered by Zariski. So this all goes back to him in some sense. So this is generated by certain distinguished open subsets. So this is supposed to be analogous to the distinguished open affines you encounter in the theory of schemes when you have a speck of a ring, right? You look at all the points where some element doesn't vanish, and that gives you another affine scheme that's an open inside. These ones you need more than one element to specify them. So you take a system of elements which satisfies a certain hypothesis, and then you look at the valuations in here such that V of Fi is less than or equal to V of G, and V of G has to be non-zero for I equals 1 through n, where F1 through Fn and G together have to generate an open ideal in A. So for example, if you take a ring with a discrete topology, then the open ideal condition is irrelevant, and basically you are, you're constructing something that is some sort of affine, especially if you take, for example, 1, comma G, then it's clear you're taking the distinguished affine defined by the element G. So one of the reasons I want to only consider the analytic case is because this definition simplifies somewhat. For A analytic, I can simplify this definition. First of all, so one characterization of analytic rings, which I haven't actually said out loud, it turns out that one way to characterize them is that the open ideals in A are actually all trivial, or all the unit ideal. And so this condition simply becomes F1 through Fng generate the unit ideal. And then, of course, if they generate the unit ideal, then this condition turns out to be unnecessary. So somehow things that generate the unit ideal, roughly speaking, can have no common zero. So you don't actually need to impose this condition because somehow if this guy were 0, then all of these other ones would be 0, and that would be bad. So that simplifies things slightly. So the topology I want to consider is the one where these form a basis of open subsets. And you can check things like if you take two of these things and intersect them, then you can represent them in terms of these guys. This thing will turn out to also have the structure of a spa. I'll tell you why in a moment. So it turns out this space is a spa of some other pair, where so B will be, I take the Tate algebra in n generators over A, and then those generators essentially become F1 over G, F2 over G, and so on. So I'm going to divide by a relation that says, well, G times T1 minus F1 becomes 0. Likewise, G times Tn minus Fn becomes 0. So I've adjoined, so to speak, F1 over G through Fn over G, and I've made sure that they are power bounded. There's one catch here, and this is going to give you a flavor of the chaos that's about to ensue. I have to take the closure of this ideal because I want to consider complete Huber rings, remember, and this ideal a priori might not be closed. So that's the wedge that's going to let all the ills of the world in, unfortunately, but no, so be it. We have to take this completion for the moment to get something complete. And there's a B plus, which I won't write down, but I can characterize it this way. So there's obviously a map from A to B, and for the right definition of B plus, I get a map like this. So a map of pairs is, of course, a map of continuous map of rings that sends A plus into B plus. I don't think we said that, but you can. One thing you'll notice is that the pluses will be kind of hanging around as ghosts during this talk, but we won't see them directly so much, but they're there. So there is a certain B plus, and so there is a certain map from this pair to this pair, which has the property it is initial among maps for which SPA BB plus maps into this subset. So you look at all the maps like this, such that, right, if you have a map of rings, then if you take a valuation here, you can pre-compose with this map to get a valuation here. So any map of pairs like this gives you a map of these sets. In fact, it's a continuous map for this topology. And this, so the condition here is that if a map has image, the map on SPAs has image landing in here, then it factors uniquely through this. And so that's a universal property. This is modeled on both the definition given by Tate for rigid analytic spaces and also the usual thing that happens for schemes. Right? For schemes, if you had a distinguished open subset generated by inverting some element G, then the corresponding thing would be just the homomorphism from the original ring to its localization where you invert G. And so by analogy with that concept, I like to call this kind of map a rational localization. It's the localization in this context corresponding to this rational subspace. So you can show that this object, together with an appropriate B plus, has this property that doesn't tell you everything you want to know. You must also check, but one checks this, well, Huber checks this, that actually the induced map from SPA BB plus to this subset of SPA AA plus is actually a homeomorphism. So this subset really does naturally carry the structure of the adic spectrum of a different pair, just like for schemes. Great. So it seems like we're in business. Now clearly the next thing to do is just construct the structure sheaf, right? Well, as usual, we start by defining a presheaf. So let me tell you what its values are going to be on these generating subspaces. So of course, I want to have the structure presheaf have its value on this rational subspace be this ring, which, if I need to refer to it without the notation of this kind, I'll write it this way. So it's, so to speak, the strictly convergent power series of A in the variables f1 over g through fn over g. That's just a shorthand for taking this quotient. Okay, so of course, technically I have to define this construction for all subsets. Remember, one of the points of this story is that we're not talking about a Grothendieck topology, we're talking about a genuine topology. This is one of the magical things about Huber's construction. So I should make a passing comment about general subsets. This works the same way as it does for schemes. So I'll just say this once and pass on. So if U is a general open, then what you're supposed to put here is, if I've done this correctly, the inverse limit of B over all of these rational localizations, where this thing is actually a subset of U. So you want the functions that on any rational subspace actually have this form. Now, if U was itself a rational subspace, then there's sort of a best choice here, which is you just take U itself, and so you don't change anything. But officially, to define a sheaf, you have to specify it everywhere, not just on some basis. So, great. So now let's recall what happens for rigid analytic spaces. So it was proved by Tate that it wasn't literally proved in this language. This was sort of Huber's reinterpretation of what Tate originally proved in rigid analytic geometry, but the content is really all in Tate's original theorem. So if A is, say, the algebra of strictly convergent power series over some some non-Archimedean field, some field complete with respect to a non-Archimedean absolute value, like QP, or any quotient thereof, then O is a sheaf. He proves more than that, but we'll come back to the extra part a little bit. Okay? So, great. If you think of Tate's theory of rigid analytic spaces as being the analytic geometry analog of the classical theory of varieties over a field, then clearly the next thing to do is just prove the analogous statement for a more general, complete Hooper ring, or Hooper pair, I should say. But then a terrible thing happens. The structure pre-sheaf, yes, it's so terrible my handwriting is starting to degenerate, but let's see if I can hold back a bit. The structure pre-sheaf is not always a sheaf. And actually, Huber already noticed this. And more recent examples that have more restrictive properties, so they're somehow even worse counterexamples, were given by Buzzard for Beckmus and Mihara. I actually don't include these examples in the notes, but I include the references to them, so you can look those up if you want. This is an unfortunate thing. So paradise is lost. So what is going on? Well, one way you can characterize this is the following result, which I haven't actually seen anywhere else, but it's in the notes, is that if O is a sheaf, then the ideal that I wrote down earlier, you can actually still see it here. Remember this ideal that I wrote down. This ideal actually has to be closed in the situation we were interested in, i.e. these elements generate the unit ideal. So all you really have to do is produce an example where this fails, and now bad things start to happen. So as I said, this was the wedge that let in this is the crack in Pandora's box. So the rest of this lecture will be some attempt to patch around this. And in particular, we need to patch around this well enough so that we can deal with perfectoid spaces. So we'll do that. Before I do that, let me make one comment. If the structure pre-sheaf happens to be a sheaf, then we can at least continue as we did before. So then we can at least give SPA AA plus the structure of a locally ringed space. It actually has a slightly richer structure because of all these valuations running around. So it's a locally ringed space. Actually, each stalk also carries a canonical valuation coming from the valuations that we used to define SPA. And then when you glue these things, these are what you call adic spaces. Okay, so provided that you have a sheaf Then we can continue with the program, take these spaces, try to put them together. You might have some questions about this, like what about cohomology and so on. We'll come back to those. Okay, so as I said, the goal for the rest of this talk is to try to salvage the situation that just broke. So the first thing I should do is give you some instances where you do actually know that the structure pre-sheaf is a sheaf. For example, the situation that Tate considered where you have an affinoid algebra over a non-Archimedean field. That's generalized by this theorem of Huber. Well, asterisk, but I may or may not want to say much about that. So if we know some sort of Noetherian hypothesis, then we can salvage the situation. So suppose I know that A is Noetherian, and in addition, all of these rings of strictly convergent power series are also Noetherian. Now, unfortunately, this is not included in the hypothesis that A itself is Noetherian. We don't have an analog of the Hilbert basis theorem for these Huber rings. I'm not even sure whether we expect it to be true. It's not quite clear. But in any case, if you assume this, which is, of course, known for an affinoid algebra by results from the classic theory of rigid analytic geometry. So if you start with this guy is known to be Noetherian. There are various proofs of this. You can either prove this with Weierstrass preparation, you can prove it using Gribner bases, you can do various things. And this applies the same for more variables, stupidly, and for quotients, or if you take the quotient and add more variables, you can compute the order of those things. So if you're in this situation where everything in sight that you can make out of A is Noetherian, then we'll say that, well, O is a sheaf, and I'll summarize that by saying that A is sheafy. Now, really I should say that the pair A comma A plus is sheafy. It turns out that actually this condition doesn't really depend on A plus. I won't explain that right now, but this is explained in the notes. So really this question of whether this structure pre-sheaf is a sheaf is a question about A, and if A has a strong Noetherian property, then everything is fine. Then we get to go back to paradise. But paradise is quite limited if we only have Noetherian things. In particular, this includes classical affinoid algebras, so rings of these convergent power series over a field, quotiented however you want. But it does not include the perfectoid rings in general. So if, for example, we take, say, a completed algebraic closure of QP, and take adjoin all the p power roots of some variable t and take the completion of that for the Gauss form, then this is not going to be Noetherian because well, the usual thing. There's an ideal that you can write down very easily that's not finitely generated. So this is not good enough. So when Huber developed this theory originally, he was mostly thinking about giving some reformulation of the theory of rigid analytic spaces that had some advantages, like the fact that it was a genuine topology, not a Grothendieck topology. But he was just thinking of that kind of situation, and so he didn't mind so much having to put Noetherian hypotheses down. But now we have a pressing reason coming from this construction of perfectoid rings and perfectoid spaces. We have a pressing reason why we would like to consider non-Noetherian things. So now we're trying to reiterate the history of modern algebraic geometry by getting away from finite type hypotheses. And this is somehow not good enough for what we need. And we've already seen that things go bonkers if you drop all hypotheses. So we need something else, and while you can directly show that perfectoid rings are sheafy, it's very nice to use the following more general result, which was, of course, inspired by the theory of perfectoids, but we're going to take it as an input, actually. We're going to reorganize the history a bit. So this is a theorem of Buzzard and Verbekmuth, again with an asterisk, that if A is stably uniform, so we saw what uniform means last time. It means that the power-bounded elements form a bounded subset. And stably uniform means the same thing is true after I make all rational localizations. So for any rational localization, AA plus to BB plus the ring B is uniform. So Buzzard and Verbekmuth give examples where this does not follow from being uniform. So this is a genuine condition on top of uniform. Then again, you show that A is sheafy. And so this includes, well, it does not include arbitrary affinoid algebras, so it doesn't completely subsume this case. Because remember, uniform rings have to be reduced. Having a nilpotent element, if you have a nilpotent element, then all of its multiples are power bounded. So uniform rings have to be reduced. And so you can't hope to deal with arbitrary affinoid algebras because there are non-reduced affinoid algebras. Just take the quotient of a ring of power series by a square of generator. But this does turn out to include the reduced affinoid algebras. I mean, it's not a general theorem that a reduced thing is uniform. That's not true. But affinoid algebras, when they are reduced, turn out to be uniform. And this will also include the perfectoid rings that we've seen earlier. So, so these are two results that are useful. Now, I'll just say a word about the asterisk without writing it down. The asterisk is because these results were proved for Tate rings, and I'm assuming something slightly weaker. There's a lemma from the work of Gaber and Romero that lets you go from Tate to analytic relatively easily, but I won't emphasize this point. So you can use this to generate lots of examples. So an example of something that's neither of these forms is, I'll just mention one other type of example that follows from this. If A is perfectoid, let's say, actually stably uniform would be enough, but so then the usual Tate algebra over that is sheafy. So this somehow follows from the fact that you can make this perfectoid version of the Tate power series. These squiggles that are indistinguishable are infinity signs. So you have an embedding like this, which splits in the category not of rings, but of topological modules over this thing, basically by discarding all the fractional powers. And this kind of argument, this kind of map lets you show that not only is this thing uniform, which was easy to see directly, but also that its rational localizations are uniform, because this structure persists when you pass to rational subspaces. So you can use this kind of construction to produce additional examples. Possibly some of the students in the project, depending on what we end up doing, might produce more examples. Okay, great. Brian, can you remind me when I'm supposed to finish?
12:30, 9 minutes.
Okay, great. Okay, so in some sense, this horrible issue of sheafiness that we've encountered is the primary obstacle. If you can get yourself past that, then many other things become less of an issue. So for example, right, one of the other things we know about the structure sheaf on an affine scheme is that its cohomology vanishes on all rational subspaces. Its higher cohomology vanishes. So the structure sheaf is acyclic. So we have an analogous result. So Liu here is going to be, I should write this out once. This is Rochuan Liu. Sorry, I can't write this in Chinese, but that's the best I can do. So Rochuan and I have been, Rochuan was my PhD student once upon a time. We've been working on this kind of thing for a number of years. Unfortunately, Rochuan was not able to be here this week. So I don't get to cite him in person, but let me mention him once. So you will see this pair of names occur a lot. You actually heard it once already. So one thing you can show in this situation is if A is sheafy, so A is of course complete and analytic, like I assumed at the beginning, but if I now also assume that the structure pre-sheaf is a sheaf, then this is already enough to see that that the cohomology vanishes whenever I consider a rational subspace U and an index I greater than 0. So you prove this by, well, I hope to have 60 seconds left at the end to allude to how the proof goes. Right? If you think about how you would do this for schemes, well, you check this, boxed myself in there, by using check cohomology. I apologize to the ASL translators. Check is, so you verify this using check cohomology. I don't know how you spell this in ASL. Right, so you verify that if you have a finite covering of one rational subspace by other rational subspaces, then the check cohomology for that covering vanishes in positive degrees. So you essentially have to make the same calculation here. It was observed by Tate, essentially. This is as refined by other people, that you only need to check, verify, the vanishing of this sort of check cohomology in the following situation. Actually, let me draw this on a fresh sheet. In the situation. So let me draw this picture. Here's X. So I take two elements, F and G, in A, which generate the unit ideal. So this space is V of F less than or equal to V of G. This space is V of F greater than or equal to V of G. And the intersection is, of course, V of F equals V of G. So you really only need to do any calculations. You can't just do this for A. You have to take a general rational subspace and then two elements. So this is actually some U. So you take some general rational subspace and you cover it by two others in this simple way. And if you can do the calculation in that situation, then that suffices to give you everything. So there's some general argument, which I won't discuss, but is very thoroughly discussed in the notes, that lets you reduce to doing this kind of calculation. Okay? And this same sort of reduction will apply to all of the other statements that are discussed in the notes, a couple of which I'll get to state, and some of which you can read about on your own. Okay? So in the last 5 minutes or so, let me say something about the last step in my program, which was, so far we have a space, we have a structure pre-sheaf on it, sometimes it's a sheaf, we know something about the cohomology of the structure sheaf. We would like to consider sheaves of modules, not just the structure sheaf. So as a quick start, let's consider finite projective modules, which should give rise to vector bundles. So for M, a finite projective A module, let M tilde be the associated sheaf. So if U is the SPA of some rational localization, then the sections of M on U will just be M tensor over A with B, which is again a finite projective B module. So it's sort of obvious from here that this sheaf is again acyclic because, well, if it were a free module, then that would be really obvious. But it's always a summand of a free module, so it's equally obvious. So note so we have acyclicity for this thing as well. And yes, let's assume A is sheafy from now on. So for the next 4 minutes, assume A, or 3 minutes, assume A is sheafy. So all these statements will require that. Okay? So then, which one I can show that if you take the category of finite projective A modules, and you form these sheaves of course can be thought of as sheaves of O modules, which are locally of the form M tilde. But the right way to talk about, say, a vector bundle on X would be not to insist that it comes from a finite projective module on the whole space, but that it comes from one locally. So there's some cover of X by subspaces, or if you want rational subspaces. It's actually quasi-compact for the topology, so you only finitely many. So you have some cover of X by rational subspaces, on each of which this sheaf is the sheaf associated to some module, and then you need to know, for basically doing any interesting calculation, that these things actually are themselves the sheaves that come from finite projective A modules. The functor going the other way being, if you have a sheaf, you take its global sections. And so it turns out this is true. And again, the way you prove this is you reduce to the simple two-element covering and show that if you have a module, if you actually have a module here and a module here, and they agree here, then you really can construct a module here that represents the whole thing. So it's again a calculation of the same flavor. Okay, finally, let me say one word about sheaves that are not projective, or modules that are not projective. So if A is strongly Noetherian, you can likewise equate finitely generated A modules with coherent sheaves. I'll just say out loud, these are the sheaves that are locally of the form M tilde, where M tilde is a finitely generated module over the appropriate ring. Now, of course, you don't expect this to work so nicely when A is not Noetherian for the usual reasons, but there's another reason. So the reason things work nice, so this was essentially due to Huber, although Huber doesn't actually quite say this, but he presumably knew this. That's correct. So he clearly was planning to write down the proof of this at some point and forgot or something. But he knew how to do it, I think it's safe to say. So here's the thing, is that if A is Noetherian, that implies that every ideal is closed. This is a consequence of the open mapping theorem in a way I won't explain. And this is actually equivalent. So this, in some sense, is the reason why Huber was able to prove sheafiness in the strong unitarian case, is because he never had problems with ideals that are not closed. We've seen earlier that is, in some sense, all of the source of the difficulty. It doesn't quite imply that Huber... In some sense, the failure of ideals to be closed is somehow all of the difficulty around sheafiness. And let me just say this. I won't use this so much in the subsequent lectures, so I'm just going to say this very briefly because I'm out of time. So you have a similar relationship between modules and sheaves for finitely generated modules, which are, on one hand, they have to be complete for the obvious topology that you get by taking them as quotients of some finite free module. That's not automatic if you have a non-Noetherian ring. And what are called not coherent, but pseudo-coherent. This means admit a projective resolution by finitely generated, or if I say finite projective modules, or finite free modules, if you prefer. So this is something stronger than finitely generated or finitely presented. It's sort of an infinite version of finitely presented. You somehow need this because you can't really deal with anything that's not finitely generated. We don't have a good theory of quasi-coherent sheaves. We can't really hope for this, at least not the way I'm thinking of it here. So we don't have a great idea about how to deal with quasi-coherent sheaves. So we would like finite generation conditions, but of course if we take kernels of maps between finitely generated things, we lose finite generation. And if we impose some stronger condition like finitely presented, we'll lose a little bit off the edge. So if we impose this condition, which I believe is, this name comes from SGA 6, it was introduced by Illuzi. If you insist that you have arbitrarily long projective resolutions by finite projective modules, then this lets you kind of work around the finite generation problems, and you can prove theorems of the same sort that I had before. You can prove an acyclicity theorem, and you can prove an equation between modules and things locally coming from modules. So I'll stop there. Thanks. There's a question in the front. Sorry, that shouldn't have never been here.
Why can't you define the structure sheaf to be just the sheafification of the structure pre-sheaf?
That's a good question. One reason is because it's not, if you take the sheafification of the structure pre-sheaf, it's not clear that gives you a complete Huber ring. It's not clear that it gives you a Huber ring at all, because the topology, that requires implicitly taking a direct limit over all possible coverings, and it's not clear that that would actually give you something with a nice topology. One exception is if SPA AA plus is covered by the SPAs of sheafy rings, then taking the sheafification does work, and it does give you something sheafy. That's a theorem in the notes. But in general, you can't completely solve this problem by just sheafifying. You can also try to solve it by doing some sort of stacky construction. The very last section in the notes talks about this sort of more functor-based way of doing things, which is, well, we'll see echoes of that in the later lectures when we start talking about more stacky objects. In the back.
So unless I'm mistaken about something, which is quite possible, we're not getting any new adic spaces considering analytic rings instead of Tate rings, but we're getting new affinoids.
That's correct. So we're not getting any new adic spaces because if you take, say, a finite collection of topologically nilpotent elements that generate the unit ideal, you can sort of take the rational subspaces where you compare them to each other, and those are Tate because you're forcing one of the things to become a topologically nilpotent unit. So indeed, from the point of view of adic spaces, you don't get any new spaces, but you do get new affinoids, which means you do get new subsets where you know things are acyclic.
Is this helpful?
It's not immediately clear that that's, it hasn't been helpful yet. It remains to be seen. This is more of an issue of kind of tidying up foundations. So yeah, it's not immediately clear that we need those extra subspaces yet, but this theory is still young. Over here, Sujatha.
Can you write down a stalk? Can you actually explicitly write what a stalk looks like?
What a stalk looks like. Okay, so the question, since it wasn't picked up, is can one say explicitly what a stalk looks like? Well, I mean, it's just the formal definition. Right? If you have X in big X, then the stalk of, say, the structure sheaf at little x, is just the direct limit of B, or say O of U, as U runs over, say, rational subspaces containing X. So this is, of course, not a Hubel ring for the same reason that I just said, that this thing does not have the topology coming from a ring of definition and a finitely generated ideal. It's just some ring. It is a local ring. I guess it's a Henselian local ring, if I remember correctly. And that property is sort of analogous to what happens in rigid spaces or Berkovich spaces. That property is crucial for a number of arguments later. Yeah, for the sections of O over some strange non-rational, right? That's just because you have to specify a structure pre-sheaf on all opens, not just the rational ones. This is sort of the usual thing you do to go from the nice formula on rational subspaces to arbitrary subspaces. Of course, you could take this limit over all open subsets containing X, but the rational ones are cofinal, so you don't need them. There's no counterpart of the localization at a point, you mean?
This is formal, right? This definition is formal.
Yeah, this definition is formal.
But the classical cases where you have definitions and then you really have an intuitive definition of what elements in the stalk looks like or what defines the stalk.
Yeah, there is something, one can say something about what these things are, but I think this is maybe a little bit out of scope for this question period. Maybe we can discuss it offline.
Okay, and that kind of ends the morning session. Except for one announcement, we have somebody whose red tablet has been misplaced somehow. So if you found it,